G'day, in this video our focus is going to be on a new concept known as specific heat capacity. In this video we're going to be covering dot point 3.5.3 and 7. We're still looking at the fifth inquiry question for waves and thermodynamics. It's again the thermodynamics part that we're focusing on. We're looking at how temperature, thermal energy and particle motion are all related. In terms of specific content, we're now going to start looking at analysing the relationship between the change in temperature of an object and its specific heat capacity through the specific heat capacity equation Q equals mc delta T. And by extension, that means that we're going to be applying that formula and that relationship to solve problems and make predictions in a variety of different situations. So our key goals for today is to first expand on the application of particle theory to temperature. So look at that in a little bit more detail beyond what I showed you in the thermodynamics basics video. Then I'm going to be defining what specific heat capacity is and how it's actually used and the relationship between specific heat capacity and other variables. And then we're going to apply that formula to some scenarios in some practice questions. So the first big concept that I want to cover today is that when we have a substance of a given temperature, we usually talk about the idea that higher particle energy means higher temperature. However, a common assumption that people probably make when they hear that is that all of those particles at that given temperature for that substance all have the same energy. However, this is not true. What we end up having is some kind of what we call Maxwell-Boltzmann distribution. And for the graph here in this example, we have two axes. The x-axis shows us the kinetic energy of particles, and the y-axis tells us the number of particles present in the substance which have that corresponding kinetic energy. So for our blue line here, T1, what that's showing us is the energy of all of the particles for a sample of iron at negative 150 degrees Celsius. What we can see here is that most of the particles have a low kinetic energy, but not all of the kinetic energy of these particles is the same. We then see that there are very, very few particles that have higher kinetic energy. In contrast, the orange line here for T2, this is an iron sample at 25 degrees Celsius, also has some particles at low kinetic energy, some particles at high kinetic energy, but on average, the majority of particles have a higher kinetic energy than the ones for temperature 1. Essentially what this means is temperatures that we measure of substances are reflective of the average kinetic energy of all of the particles that are there. Some particles will have energy which is higher than the average, and some will have energy which is lower than the average. But when we put that all together, they average together to have some sort of energy which is then converted to or reflective of a temperature. Now for the key part of this lesson, looking at specific heat capacity. By definition, we can say that specific heat capacity is the energy required to raise the temperature of a specific mass of a substance by 1 degree Kelvin. Generally, that specific mass is a kilo, so it's the energy required to raise the temperature of a kilo of a substance by 1 degree Kelvin. We could do some unit conversions here and look at the energy required to raise a gram of a substance by a Kelvin, etc., etc. But generally speaking, when we're looking at specific heat capacity, we're focused on a kilo of a substance. Here I have a table showing some different specific heat capacities for some common substances. They're all measured in joules per kilo per Kelvin. In other words, how many joules is required to raise your substance by a degree Kelvin for every kilo which is present. It's really important to note that this information is not in your data sheet, with the exception of water, and I'll be showing you that in the next slide. What that means is if you have to do any kind of specific heat capacity related question that doesn't involve water, if it's some other substance, the values must be given to you unless the question is specifically asking you to calculate for the specific heat capacity of a substance that's not water. So our specific heat capacity formula we can find in the waves and thermodynamics part of our data sheet. It's right at the bottom. It's Q is equal to mc delta T, where C here is the specific heat capacity of water, which is 4.18 times 10 to the 3 joules per kilo per Kelvin. So C here in this equation is the specific heat capacity. Again, this is data that is given to you. Technically, if they're talking about water, they don't need to give you that data because it is in the data sheet. However, for any other substance, if we're looking at its specific heat capacity, we use the data that is given to us. Q is the energy that is being absorbed or released by the substance. M is the mass of the substance. And delta T is the change in temperature that the substance experiences when the energy is applied to it or the energy is being released from it. Energy is being measured in joules. Mass is being measured in kilos. Change in temperature is being measured in degrees Kelvin. Remembering though that a change in degrees Celsius is the same as degrees Kelvin, so if you do have a question that's in degrees Celsius, you just take the difference anyway, and those numbers should work out. Specific heat capacity, again, is joules per kilos per Kelvin. This is the units of measurement that should be given to you in a question. Just bear in mind, if the specific heat capacity was, say, given in joules per gram per Kelvin or something like that, what we would need to do is make sure that the unit in the specific heat capacity data that you are substituting in matches with the units of measurement that you're subbing in from all of your other variables here. Last thing to note is that when you are substituting into this equation, you must make sure that all substitutions are for measurements that correspond with the same substance. So for example, if you're looking at a change in temperature for water, then the specific heat capacity, mass, and energy that you substitute in are all for water. If there's some other substance, all measurements that you're substituting in must match that same substance that's undergoing some sort of change in energy and thus change in temperature. So our first practice question here, we have a 0.562 block of iron at 25 degrees Celsius being heated up to 30.13 degrees Celsius. We need to calculate the energy absorbed by the iron. Now to solve this, the first step that I'm going to do is to draw up a data column. Just some quick things to note for the change in temperature. I calculated that by taking the final temperature and subtracting the initial temperature. Also note that I converted my change in temperature from degrees Celsius to degrees Kelvin. All I needed to do was flip our units of measurement. No actual conversion needs to be made because an increase in Kelvin is the same as an increase in Celsius. Also, I've gotten my C value here, 450 joules per kilo per Kelvin, from the data in the previous table here, where we can see that is a specific heat capacity for iron. So to solve for Q, we know from our specific heat equation that it's equal to mc delta T, which means all I need to do is substitute. Notice for my solution that I've given a final answer, which is 1,300 joules. That's correct to two significant figures, and that matches the number of significant figures given to us for our specific heat capacity for iron. In our second question, we're told that the same block of iron cools, releasing 1.154 kilojoules of energy, and that we need to calculate the temperature of the block. First step again is to identify all of our data and construct a data column. Something else to note is that I converted my Q value from kilojoules to joules, again to ensure that I'm matching the units that we have for our C value, our specific heat capacity of iron. Something else to note here is that because we are releasing energy in this problem, what that means is that the Q value here should be negative, that energy is being removed from the object, therefore there is a loss of energy, and we represent that with a negative value. From here, what I need to do is calculate for delta T, and I'm going to do that in order to be able to find the final temperature at the end. To calculate for delta T, we just need to use our Q equals mc delta T formula, rearrange for delta T, and then substitute. So from this data here, what we can see is that the block of iron will cool, reduce its temperature by 4.56 degrees Kelvin. We know that in the first step, when it finished heating, that its temperature was 30.13 degrees Celsius. That's the initial temperature. I now have all the data that I need to be able to calculate for the final temperature. My final answer here is that the final temperature of the iron block will be 26 degrees Celsius. I've given that answer to two significant figures, again, to match the number of significant figures of our specific heat capacity of water. In our final question for today, we have a 436 gram chunk of hot copper that's being placed into a bucket of water, which has 3.34 litres of water at 20.93 degrees Celsius. We're told that the two objects are going to reach thermal equilibrium, and they're going to do so at a temperature of 24.5 degrees Celsius. Our job is to calculate what the beginning temperature of the copper was before it was placed into the bucket of water. Here in this question, the big concept to have a mathematical statement that actually works and allows us to calculate for this is that the energy of the copper that's being lost is going to be all gained by the water. And that can be written as the energy of copper which is lost is equal to the energy that the water gains. So in a sense, QC is equal to QW. At least they are equal to each other by magnitude. However, in this mathematical expression, we do need to show that energy is being lost in one and gained in the other. So what that really means is that the negative of QC is equal to QW. What we can then do is substitute in MC delta T into both sides, and that's going to allow us to be able to analyze what's actually happening to the temperature of the copper. So in this problem, we want to solve for delta T for copper, and that can be done by rearranging our equation and making that variable the subject. Now, before we substitute, I'm just going to extract all of the data that we have from the question so far and draw that up into a data column so that we ensure that we substitute all of our values in correctly. So some things to note here as I put this data column together. First off, I have converted my mass of copper into a value that's in kilos because we're working with specific heat capacities where kilos is a part of those units. I found the specific heat capacity for copper again from that table in the previous slide. The mass of water here I've written down as 3.34 kilos. I'm assuming here in this problem that the density of water is going to be exactly 1 kilo per litre, meaning that the number of litres of water is going to be equivalent to the number of kilos present. And for the change in temperature of the water, I've just done that by taking the difference between the final temperature and the initial temperature. From here, we can substitute and calculate. And the answer that we should get here is negative 300.8 degrees Kelvin. What that means is that the copper dropped its temperature by just over 300 degrees in Kelvin to get to its thermal equilibrium temperature of 24.5 degrees. From here, we now have all the information to be able to calculate for its starting temperature. And as the final result here, I've calculated that the initial temperature of the copper, it was about 330 degrees Celsius. I am giving that answer to two significant figures. Again, that is going to match our lowest number of significant figures that we had in the question, and that was for the specific heat capacity of the copper, which only had two significant figures there in it. Thank you very much, everyone. In the next video, we're going to begin to unpack thermal conductivity in a little bit more detail. But until then, have a good one.